All right, so let's start by addressing the elephant in the room, the exam scores. So I have everybody's names filtered off to the side so that we can't see things. I just want to point a couple of things out here because there have been some questions. So there were not any problems that had abnormally low correct response rates to indicate that there were issues with the test. If we look here at problem number 7, the correct response rate was 41%. Which is a little bit low. However, over here in this column, this is the partial credit, which 17% got that. So if you add those together, well over half of the students wound up getting either the right answer or the right answer with the wrong sign, which means they just didn't understand the passive sign convention part of it. Kind of a similar thing over here for problems 22 and 23, which were, in my opinion, the hardest questions on the exam. For problem 22, 28% got the correct answer. An additional 17% got the correct answer with the wrong side. Add those together, 45%. Nothing that would indicate that there was an error. And also I worked it out and all that kind of stuff, and I'm right. Same thing for problem 23, which was just the second half of problem 22. 33% plus 17, or excuse me, 11% comes out to be 44%. So a little under half of you guys got it right as a whole, but I mean, that's the hardest problems on the test. In our section, the highest grade was a 105, of which there were, I believe, I see 3 of them off the bat. I thought there were maybe 4, but anyway. So the scores in our class ranged all the way from a 12 to a 105. In other sections, it's ranging from, it looks like, there's a 22.5 all the way up to a 103.5. In section 3, there's a 21, I think is the lowest. And 94.5 may be the highest. That's odd, but anyway. So if we go over here to the key, we can see the averages and all of that kind of good stuff. So section 1, which is our section, the average was a 68.22. Realistically, that's about 5 to 7 points lower than I want it to be. That being said, it is effectively 8 points higher than what the score was on almost this exact same test last quarter. I literally made a change to a single problem. So for those of you that are repeating the class and saw your scores significantly improve, that's awesome. It means you're understanding material a lot more because it's an apples to apples comparison. Section 2, the average was a 58. Not great, but still literally better than the overall average last fall. Section 3, just shy of a 61. So while I legitimately think that the scores overall should be higher, I commend you all for crushing my enemies. It wildly pisses me off when my section doesn't score the highest, and the fact that we beat the other sections by 7.5 points makes me incredibly happy, so great job. All right. For what it's worth, I believe this is the hardest material in the class that we've covered. I hesitate to say hardest, actually. It's the most different material. So we covered the most amount of material for this test. So for exam 2, typically speaking, the scores on that exam are significantly higher because realistically, exam 2 covers Thevenin and Norton equivalent circuits, inductance and capacitance, which we're going to cover, which we're going to cover the next couple of days, and then transient analysis of first order systems. And that's it. It's really just 3 topics. Whereas for exam 1, we covered 8 distinct things, right? Exam 3 is just the exact same stuff that we covered in exam 1, except using complex numbers. So that's the first half. And then the second half is just power relationships, for which you actually get an equation sheet. So if you know how to use your calculator and you've gotten good at the exam 1 material, exam 3 should be easier than exam 1. So I truly believe exam 1 is the hardest exam in this class. So if you did well on exam 1, you're doing great. If you did less than well on exam 1, wait until you see how exam 2 shakes out before you make any sort of decision. The way that the grades are structured in this class, if you're doing all of your homework, mini labs, and in-class assignments, if you scored higher than a 34, it is still mathematically possible for you to make an A in this course, which the overwhelming majority of students scored higher than a 34. So there's really no reason for anybody to be freaking out just yet. If you scored particularly poorly, it just lets you know you need to adjust how you're studying, all that kind of good stuff. Not to be a jerk about things, but I can definitely say that the overwhelming majority of students who had scores less than 40 are the students that we don't see here today, which kind of makes sense. But anyway, so if you have a friend who's enrolled in this class, tell them to, I don't know, maybe show up. They might learn something. All right. Any questions about the grades or anything like that? And obviously I can't answer questions about individual grades. Okay. All right. So today we are going to be talking about inductance and inductors. So let's start by looking at what an inductor is. And the short answer is it's a coil of wire. We can form that coil of wire in a couple of different ways that are quite common. So we're going to look at those really quickly. They're going to inform our behavior of these devices in some way as well. So for our first example, let's say that we start with a cylindrical core, where this red thing right here is what's going to be called the core material. And it does play some role in the behavior of an inductor. And then around this cylindrical core, we are going to wrap a wire. Like so, where this wire has some number of turns also related to how the device behaves and all of that kind of stuff. This is an example of a solenoidal inductor. And then over here on the right-hand side, and you're going to have to bear with my inability to draw a circle to save my life here, we are going to have what's called a toroidal inductor. So here is our core material, once again in red. And I'm going to take a wire like so. And wrap it around this toroid or donut shape to form an inductor. Here are my terminals. So these are the most common shapes that are utilized whenever we're trying to implement some sort of inductance. But really, any closed path has some inductance associated with it. It's usually just so small that we don't care about it. Okay. How many of you guys have had physics 202? A handful of you guys. Great. All right. So if I have, this is a separate thing down here. a long section of wire that's carrying some steady current I should have a magnetic field. How does the magnetic field look for a long straight section of wire? Some will be into the page, some will be out of the page. How do we tell what direction things have? The right-hand rule. So if our thumb, Ashton's throwing gang signs at me because I taught her field theory, gosh, forever ago at this point. If our thumb is in the direction of current flow, our fingers wrap around in the direction of the magnetic field. So if our current is flowing from left to right, then above our wire, our magnetic field lines should be coming out of the page, which I'm going to indicate as this circle with a dot in the middle of it, which is intended to look like the head of an arrow coming at you. And below it are arrows directed into the page, where this is like you're looking at the ass end of an arrow or the fletching or whatever you want to call it. Okay. So why I'm bringing this up is that we're obviously going to be passing currents through the wires in our coils here. And what we'll see is that we're going to generate a magnetic field inside of these core structures, okay? So based on the direction of the windings, our field lines are going to be in the up direction. So this green line here is going to be magnetic field, and also the direction of our magnetic flux, which we'll talk about in a moment. And that's what the green lines represent on both sides. So what the coils do is they tend to, I hate to say amplify because that's not really the right word, but they confine the flux or like compress the flux to make it in one particular area. And the magnetic flux is actually the energy storage mechanism of an inductor. Inductors are used as temporary energy storage elements because, as we'll find in a little bit when we explore the math, the current flowing through an inductor cannot change abruptly, meaning that if the inductor is carrying some amount of current when you have an applied voltage across it, if you turn that voltage off, it'll still carry that same amount of current for a small amount of time before it gradually discharges. So its job is to inject current into the system when a change happens. And that's governed by what's called Faraday's law of induction, which if any of you have had Physics 202, you probably know about. And if you haven't had it yet, we're going to talk about it very, very briefly here in a couple of moments. Okay. So the flux inside of the core is dependent upon the amount of current that is passing through the coil by the following relationship. Magnetic flux, whose symbol is phi b, is equal to the inductance, whose symbol is L, multiplied by current, whose symbol is I. And so from this, we can define inductance L to be the ratio of the magnetic flux phi b divided by the current I that is causing the magnetic flux to occur, because we don't get magnetic flux unless we have some current that's generating a magnetic field. So from a dimensional standpoint, magnetic flux is measured in what's called a Weber. And as hopefully we're all aware, current is measured in amperes. A Weber is nothing more than a volt second. So we have volt seconds per amperes. We could just as easily call this an ohm second, but we usually give it a special name, which is the Henry. or H. Okay. So I personally learned this as 1 Henry is 1 volt second per ampere. And that's the conversion factor that you'll see me use whenever we're dealing with the math behind things here. Okay. Our inductance as a word definition is the ratio of the change in magnetic flux of an element due to a corresponding change in current. So effectively for inductors, magnetic field, and by extension, the magnetic flux is the most important thing that's going on. And when we talk about capacitors in our next lecture, we'll find that it's the electric field is the most important thing. We're going to see that our relationships for capacitors, inductors, and all that kind of stuff are almost exactly the same, or not, yeah, so they're almost exactly the same, except that current and voltage are switching places. Other than that, the relationships are literally identical because these two things are electrical duals. They perform the same role in circuits, meaning they're both forms of temporary energy storage. But because in one of them, it's the electric field that's storing the energy, everything is related to the voltage. And in the inductance, because it's the magnetic field that's doing everything, everything is related to the current. All right, so now let's get into our current voltage relationships and all of this kind of stuff, okay? So circuit characteristics of an inductor. So the schematic symbol for an inductor is a coil of wire, because that's really all an inductor is. You could also think about it kind of as looking like a spring, which is actually pretty darn handy because in the mechanical equivalent circuit analog, a spring plays the exact same role as an inductor does. Capacitors are your, let's see, so like in a mechanical resonating circuit, the spring is your inductor, the capacitance is the proof mass, and the mechanical damping is the same thing as the resistance. So you can tie it all back to your mechanical engineering classes if you so choose. But anyway, same equations govern everything. So our inductor is going to exhibit some inductance L that we've already defined. We will have a voltage drop across our inductor, which I'm going to call VL of T. And let's say that our current IL of T is flowing into the positive polarity terminal, so that this particular inductor is assumed to be absorbing power because the passive sign convention is obeyed. Okay. So I'm going to hit you guys with an equation here. And it is EMF, E, is equal to negative the derivative of the magnetic flux with respect to time, like so. This is Faraday's law of induction from Physics 202 and any field theory classes you might have had. Let me explain it to you in the simplest forms. An electromotive force is literally just a force that's capable of moving charge around a path. It is the exact same thing as a voltage, or a voltage is an example of an electromotive force would be a better way to put that, okay? So this guy over here on the left, this E, is really just the voltage drop across the inductor. If we have a time varying flux, we will induce a voltage across our coil, is what that equation says. And the polarity of the voltage induced is such that the change in flux will be minimized because we don't want the flux to change. Nature hates change. So all of our induced quantities will be in such a way so that the amount of change that we experience is as small as it can possibly be, okay? Our magnetic flux is related to our current through the inductance, which we learned about a moment ago, right? So if we have VL is equal to negative the change in, sorry, we're using a different symbol for B that I was, so let's change that. We know that phi B is just L times IL. So this is going to look like L times the derivative of our current with respect to time. The negative sign here has gone away. And I'm just going to do some hand waving to kind of get rid of it. It's due to what's called Lenz's law, which is telling us the direction of the induced voltage and current are going to be in such a way as to maintain the constant level of flux. But now that we're not going to care about what the flux is doing anymore because everything is related to just voltage and current, we don't really need to pay attention to that. Okay. So I understand completely that there's a negative sign that seems to have magically disappeared. That is on purpose. Lenz's law takes care of it. And once you get to physics 202, you'll understand that statement a little bit more. Okay. So we now have our first equation. Okay. The voltage drop across an inductor is equal to the inductance times the derivative of the current flowing through the inductor. Now, there are two very, very important consequences of this particular mathematical statement, okay? So the first one is in a DC circuit, an inductor behaves like, and I'm going to leave this blank, we're going to talk about it. So in a DC circuit, that means that all of our voltages and currents are constant value, okay? So if we have a constant current, what's the derivative of a constant current? 0. So what's L times 0? 0. So the voltage drop across our inductor in a DC circuit must be 0 because L times the derivative of the current is 0. What do we know of that always has a 0-volt drop over it? A short circuit. Absolutely right. So in a DC circuit, an inductor behaves like a short circuit. So effectively, in a DC circuit, inductors don't do literally anything. They don't absorb any power or anything like that because the voltage drop across them is always 0. So they're not really storing any energy, or I can't say that because stored energy is based on the amount of current flowing through it. But they're not absorbing any power or anything like that, steady state or anything, okay? So you would definitely have a homework problem that involves a DC circuit with a bunch of inductors in it and all that kind of other stuff. You're expected to literally just short those inductors out and then use the exact same circuit analysis techniques that you had been using to figure out all the other quantities. It's literally just there to remind you, in a DC circuit, these guys get shorted out. The other consequence of this first derivative-based relationship is going to take a little bit more explaining to do, okay? So I want to look at something here really quickly. This is arguably an example. Let's say that we have, to make the math as easy as possible, a 1 Henry inductor, which is quite large, but doable. And this is the voltage drop across our inductor. And this is the current flowing through our inductor. And then over here, I'm going to put a graph where this graph will be the current flowing through the inductor as a function of time. And I want us to determine the voltage drop across the inductor as a function of time. So let's start with something like this, where our current linearly increases to, let's say, 5 amps over 2 seconds, stays 5 amps for 2 more seconds, and then linearly increases back down to 0. And again, a 2-second interval. What would we expect our voltage to look like? Voltage is L, which in this case is just 1 to make the math very, very easy, times the derivative of our inductor current. So the derivative of this graph is going to be the slope at each of these intervals, right? So over the interval from 0 seconds to 2 seconds, what's our slope? 5 halves or 2.5, okay? So 2.5 amps per second times our inductance of 1 Henry, where a Henry is a volt second per ampere, is going to come out to be 2.5 volts. So we're going to see that we have 2.5 volts until we hit time t is equal to 2. Then our current is constant. So what should our voltage drop across our inductor be? 0. So it's going to drop abruptly down to 0, and it's going to stay 0 until we hit t is equal to 4 seconds. What's our slope over the interval from 4 seconds to 6 seconds? Negative 2.5, which means our voltage will drop down to negative 2.5. And then once it settles at t is equal to 6 to 0 and stays 0, it'll go back to 0. Okay. So whenever our current is increasing, our voltage is positive. Whenever our current is decreasing, our voltage is negative. And the amount of time it takes for our current to change from one state to the other is going to impact the size of our voltage that we observe across our device. So if I were to look at this waveform, hopefully you guys can see the difference between the pink and the red. Effectively, what I'm saying here, what I'm trying to say is, what would happen if the current changed twice as quickly? What should we expect the voltage to do? Double, right? So we would expect our voltage to be at +5, which I'll put up here, 0, -5, which will be down here somewhere. Yeah. What happens? I'll do a new graph here because that one's getting rather busy. If we have a situation like this, where our current is 0 for 2 seconds, instantaneously jumps up to 5, instantaneously drops back down to 0, like so. What would we expect our voltage waveform to look like? Absolutely. So Camden has correctly figured out that the derivative of our transition is infinitely large in one direction and negative infinity in the opposite direction. Effectively, we're going from 0 to 5, so that our slope would be 5 minus 0 divided by 2 seconds minus 2 seconds in this case. So 5 over 0 is infinity. So what we would see is a voltage impulse at t is equal to 2 seconds. And then when our current transitions from 5 back down to 0, we would see a negative voltage impulse at 4 seconds, where an impulse literally is just a mathematical thing and a thing we see in electrical engineering a lot. That means it's got infinite height, but 0 duration. Okay. So let me ask you guys a practical question. Can we have an infinitely large voltage? Of course not, right? Because an infinitely large voltage would mean that we have transferred an infinite amount of energy in an infinitesimal amount of time. Physically cannot be done. So what does that tell us about the behavior of an inductor? Our current can't change instantaneously, because if it does, we get an infinitely large voltage. Okay? So we're going to summarize this by saying the current through an inductor cannot change abruptly. And I'm going to give you a little mathematical notation here that we're going to use very frequently in this class. So I'm going to say the inductor current at some time t minus, meaning I'm just approaching some arbitrary point in time from the left, has to equal to the inductor current at time t plus, meaning we're looking at that exact same instant in time, but approaching it from the right. Are you guys familiar with the plus and minus notation for your math classes? All that kind of stuff. So all I'm saying here, if t is 0, IL at 0 minus, so the instant in time directly before 0 has to be the same thing as the instant in time directly after 0. Cannot change abruptly. It can change in nanoseconds or microseconds or femtoseconds or something like that, but it just cannot be an instantaneous change in time. Okay. All right, so just to recap things here, we have our first derivative-based relationship, and from that we gleaned two very important pieces of information about the behavior of an inductor. The first of which is it behaves like a short circuit in DC circuits, and in an AC circuit, meaning where our currents are changing, the current through an inductor cannot change abruptly. Okay. What we're going to do now is we are going to just literally rearrange our first equation to get a second relationship. Okay. So if we start with VL is equal to L di by dt. Well, Elizabeth, I believe your second major is math, so you're going to be really pissed off about what I'm about to do, but that's okay. I'm going to multiply both sides by dt, giving me L times the derivative of IL is equal to VL by dt. Now I'm going to divide both sides by L so that I have 1 over L here. And to get rid of that derivative in front, I'm going to take the integral of both sides, where this integral is going to be from negative infinity to t. Because I have t as my variable and t is in the limits of my integration, I'm going to call this guy here t prime, which is just a dummy variable representing time. Okay, it does not mean do a derivative. So this is our second relationship, but we are going to play with it a little bit further because we don't always know what's happening at negative infinity, right? or we realistically don't usually care what's happening at negative infinity. So we can say that this reduces to, or I guess really expands to, 1 over L times the integral from T naught, where T naught is just a point in time where the inductor current is a known quantity, up to our time of interest T, times, so the integral of the inductor voltage with respect to time, plus IL at T. I want to point out here, because I've been asked about it before, that term there at the very end, IL at T naught, that is not inside the integration. That is just adding a constant on at the end. It represents the initial condition on the inductor current. So let's, this will be relationship number 2. Let's explore this briefly. So let's say that we have a circuit here where we have a time varying voltage applied across an inductor, like so. And once again, for the ease of math's sake, let's say that this inductor value is 1 Henry. We are trying to figure out what our inductor current is as a function of time. And let's say that Vs of t looks like this. So at t is equal to 0, it has a value of, let's call it 8 volts. At t is equal to 2 seconds, it abruptly drops down to 0 and stays at 0. So one thing that I want to point out here is Vs of t is obviously the voltage drop across our inductor as well, because it's just 2 elements connected in parallel. The voltage drop across an inductor can absolutely change abruptly. It is only the current that cannot, okay? So this is a perfectly acceptable thing. We could do this by using a square wave generator from our function generators over here around the classroom and just connect an inductor and see something like this, okay? Let's also say that IL at 0 is 2 amps. And we are interested in figuring out what IL of t is for time greater than 0. So if we are using our equation, for inductor current, we would have something like this. So IL, actually, hold on. Let me take one quick step back here. We could express our inductor voltage VL of t as a piecewise function, where it has a value of 8 seconds over the interval from 0 is less than t is less than 2 seconds. And then it has a value of 0 volts for t greater than 2 seconds, like so. Because we have a piecewise voltage function, we're going to have to break our integral up into 2 parts. So we would have IL of t will be equal to, I'm going to put square brackets around this guy, 1 over L. So that's 1 over 1 Henry, where a Henry is a volt second per amp. So I'm just getting the units here taken care of. Times, let me move this bracket over here because I'm going to distribute that thing. The integral from 0 seconds to 2 seconds of 8 volts with respect to time. Why I'm hesitating here is because I want to know what it's doing over this interval, not just what its numerical value will be. So I'm actually going to call that top limit t, and I'm just not going to let t get up to 2 seconds so that I get a function at the output of this thing. Okay. Plus 2 amps, which is my so plus 2 amps, which is my initial condition. So if we do the math here, hopefully we can see that the 8 volts will just pop out. And so that's going to look like 8 volts times amps over 1 volt per second. So those volts cancel each other out. How do I take the integral of dt? Just t. So then we're going to have t prime evaluated at t and 0 plus 2 amps. So that's going to look like 8 amps per second multiplied by t measured in seconds minus 0 plus 2 amps. So let's plot this thing real quickly. So we're starting at 2. Do that one in red, yeah. And then we're going to be increasing at a rate of 8 amps per second. So after 1 second, we should be at 10. And after 2 seconds, we should be at 16 plus 2, so that'd be 18. So this is not going to be remotely to scale, but let's say that we have 18 amps up here. And we have a simple linear increase like so. Where this is 2 seconds. Now let's figure out what's going on over our second interval, all right? So for this, we're going to have IL of t is equal to 1 over L times the integral from 2 seconds to some later point in time, which doesn't particularly matter, times 0 volts dt prime plus whatever IL was at 2 seconds, which we figured out was already 18 amps. What should happen to this integral then? 0, because we're integrating 0, right? So this whole term right here goes to 0, and we're just left with the 18 amps. So our current will stay constant effectively forever, supposedly. Now, if we were able to have an ideal inductance, that would be true. So what I mean by an ideal inductance is an inductance that doesn't have any resistance or anything like that associated with it, which is literally practically impossible because wires have some finite amount of resistance. In truth, what we would see is that our inductor current would gradually exponentially decay towards zero as all of the energy stored in our inductor got converted into heat by the resistance of the wire, which is exactly what we're going to be talking about on next Monday's class when we deal with transient analysis. Okay, but we can see pretty easily here, I hope, that an inductor, a ideal inductor at least, can behave as an energy storage element because it has some amount of current flowing through it, even when we turn the voltage off. Okay, that's what I'm trying to illustrate with this example here. So, speaking of using an inductor as an energy storage element, now let's talk about the power absorbed by an inductor and the energy stored by an inductor. Okay. So these are where our third and fourth relationships are going to come from. Okay. So let's talk about the power absorbed by an inductor. Anybody have any thought where our jumping off point for this discussion is going to be? What's power? V times I. Absolutely right. And that's exactly what it's going to be here, right? So the voltage drop across the inductor multiplied by the current flowing through the inductor. This is true. Absolutely true. However, we know that the voltage drop across an inductor is related to the current flowing through the inductor. So we can make a simple substitution here. Effectively, we're going to substitute in equation 1, and this is going to give us L times the inductor current times the derivative of the inductor current. That is also a way to calculate power. And there is relationship number 3. If I'm being entirely honest, I would say 95% of the time I wind up just using I times V because that winds up being easier than taking derivatives and all of that kind of junk. But this other relationship is technically true. Okay, now let's look at energy. Okay. So the energy stored by an inductor is simply the integral of the power. So let's start our integration at -infinity, and we'll integrate up to some point in time t, and we're going to integrate PL t prime dt prime like so. And then I'm going to substitute in my power relationship that we just derived. -infinity time of L IL PIL by dt. All of these t's should be primed, and then I'll have a dt prime there. Okay. So again, Elizabeth, I'm apologizing that we have a math major here, so I'm about to do some engineering math. I think dt over dt is 1, so they can cancel each other out because, again, I'm an engineer and I don't care. So now I'm integrating with respect to my inductor current, which means the limits of my integration need to change to reflect that. So this is going to look like us integrating from IL at t is equal to -infinity up to IL at our time of interest, L IL DIL. Well, let's say that at the beginning of time, which is what negative infinity represents, our inductor current is 0 amps because it's impossible to pass a current through something before electricity is invented. Okay? So we're just arbitrarily saying that at the beginning of time, the current flowing through our inductor, so the moment it was created, is 0. Okay? The L is a constant, so I can move that out. And so I'm effectively integrating IL with respect to the derivative of IL, or putting it in more simple terms, what's the integral of x dx? X squared over 2, right? So IL squared over 2, or 1/2 L times our current squared. This is our energy stored by an inductor relationship, which is relationship number 4, which is making an assumption here, technically, that there was no current flowing through the inductor at T is equal to negative infinity, which is an easy assumption to make. All right, so just to recap things, today we learned the following relationships for an inductor L that has a voltage drop VL across it and a current IL flowing through it. Number 1, the voltage drop across the inductor is just L times the derivative of the current flowing through the inductor. Relationship number 2 is current flowing through the inductor is just 1 over L times the integral from negative infinity to some point in time of VL T prime dt prime, or IL at T naught, the T of VL T prime dt prime plus IL of T naught. We also learned that the power absorbed by our inductor is the voltage drop across our inductor times the current flowing through our inductor, or L IL EIL by dt. And lastly, the energy stored by an inductor is 1/2 L on IL squared. So those are 4 of the, I think in total, 10 total equations that I'm going to expect you to have learned by your next exam. Okay. I'm telling you right now, these 4 equations will be on your test, 100%. Expect a theory question asking you which of these equations about blah, blah, blah is correct. It's going to show up, okay? And you'll see that if you look at the practice. So I'm just giving you fair warning that it's going to happen. All right, so let's put these equations into utilization. Let me go way the hell back here and find a good example. Okay. So let's say that VL of T can be expressed as a piecewise function where we have 0 volts for T less than 0 and 5e to the negative 4t volts for T greater than 0. Let's say that L, actually, let me just draw this. is 250 millihenries. This is the voltage drop. This is the current. And just to clarify something that I know somebody's going to ask a question about in a little bit, this 4 here is actually 4 per second. So it just has units of per second so that the exponential function is acting on a dimensionless quantity so that we're just getting a voltage here. Okay. So on your exams and all that kind of good stuff, I typically say, and you might have noticed this, some number e to the alpha, where alpha is equal to 5 per second or something like that, so that it's incredibly obvious what you're supposed to do with the unit when you do the derivative and all that kind of jazz. Just pre-answering that question. Okay. If IL of 0 is equal to 2 amps, I want us to determine A, our inductor current, IL of t. So I'm looking for a function here. B, the absorbed power of the inductor, PL of t. Also looking for a function. And C, the energy stored by the inductor, WL of t. And all of these quantities are for t greater than or equal to 0. So this is one style of questions I very much like to ask on your exam. Okay. And it's just literally here to reinforce all of the different relationships. Okay. So in this particular problem, we were given inductor voltage and were asked to find inductor current. So which of our 4 equations should we use for part A? Second equation. Okay. So for part A, we know that IL is equal to 1 over L times the integral. We have some defined T naught where our current was known. So we're going to use that second version from 0 seconds to T of VL T prime, BT prime, plus IL at 0. Substituting numbers in here, 250 millihenries is the same thing as 1/4 of a henry. And since we're taking the reciprocal of that, I'm going to say that this is 4 over 1 because that's the reciprocal of 1/4. And my units, because I have henries in the denominator, is going to look like volt seconds in the denominator and amperes in the numerator. So that's me literally just going from henries to volt seconds or amperes to make things work out so that I'm going to have amps in the numerator because I'm trying to find the current. Okay. One of the most common mistakes I see students make in doing this work is not paying attention to the units, and so they wind up getting lost in trying to figure out what's going on. So I am going to be extraordinarily, to the point of annoying, particular about units for the next couple of days. Now we're going to integrate from 0 seconds to T. Our expression, 5e to the negative 4t prime dt prime. Actually, I'm just to be annoying about the units, I'm going to write this as 5 volts e to the negative 4t prime dt prime, like so. And then I'm going to add to this my 2 amp initial condition current. So hopefully it's pretty darn obvious that I can just move the 5 volts outside of my integration because it's a constant. How do I take the derivative of e to the something. So I heard Camden say it correctly. I am going to do it out here to the side just to remind you guys of what's going on, because these are relationships that I'm going to expect you to be able to do. The derivative of e to the alpha t is alpha e to the alpha t. The integral of e to the alpha t dt is 1 over alpha e to the alpha t plus c. In this case, alpha is just -4. Okay? So we're going to have our 4 amps per volt second. I'm going to pull my 5 volts out. Now I'm performing that integration, so I'm going to pull out a 1 over alpha. So that's going to look like 1 over -4 per second. Then I am going to have e to the -4t prime evaluated at 0 seconds and t. And to all of this stuff, I add 2 amps. Is my math clear? And I'm probably doing this too slowly for most of you, but there are some people who are going to need this level of detail to make sure all the units and all that kind of stuff are working out. Yes, sir. So let's look at what the units are doing, John. No, there's no reason to apologize whatsoever, because I was about to cancel all these out anyway. Okay. So I have volts in the numerator is going to cancel volts in the denominator. So those guys are obviously going to cancel each other out. I have seconds being multiplied by per second. So those cancel each other out. And I'm left with just a current measured in amperes, which is exactly what I would expect because it's a current. Okay. We can also pretty easily see that this 4 and this 4 wind up canceling each other out. So I am left with -5 amps. So e to the -4t prime evaluated at t is just e to the -4t minus e to the -4t prime evaluated at 0. So what's e to the 0? 1. This is another very common mistake that I see students make. They'll just say, oh, we're evaluating at 0, so call it 0. That's wrong. E to the 0 is 1. Plus 2 amps. And now we can just do a little bit of rearranging to get rid of our negative signs and all of that kind of stuff. So this is going to look like +5 amps plus 2 amps. So let's call that 7 minus 5e to the -4t, where everything is measured in amps. So that is our current. I believe I have showed you all of the nuance of the units, as well as how to properly use the initial conditions and all of that kind of stuff in this here particular thing. All right. So anybody have any questions about our answer for part A? John. Okay, so let me go back up here to the top. 200 millihenries is the same thing as 1/4 of a Henry. 1/4 of a Henry is 1/4 of a volt second per ampere. And because I have 1 over L, I just put the reciprocal of that thing up there down here. Yep. And flipped it all over because that's how reciprocals work. No problem. Any other questions regarding the determination of our inductor current here? All right. So this one I hope will be less annoying. For part B, we want to find the power. So which representation of the power should we use? Should we use V times I or L times I times the derivative? V times I will be easier now that we know V and I, right? So let's make our lives easier. So the power absorbed by our inductor is just going to be VL times IL. So that is going to be 5e to the minus 4t volts times 7 minus 5e to the minus 4t amps. So 5 times 7 looks like 35 e to the minus 4t. Volts times amps is watts, so that's all going to be okay. 5 times negative 5 is negative 25. So what happens when I multiply e to the negative 4t times e to the negative 4t? I add the arguments of the exponential functions together. So negative 4 plus negative 4 is negative 8. Call it a day. That one's done. For part C, we need to find the energy stored by our inductor, which is just 1/2 L times our current squared. So that is going to be 1/2 times 1/4 of a volt second per ampere times 7 minus 5e to the negative 4t amps, quantity squared. I forgot to write the E. Yeah, thank you for that. Nope. There was supposed to be an E there. I just put the argument of the exponent or the exponential function and forgot to write the exponential function itself. So thank you for that, Ashton. I can see why people would be confused. So let's play around with this really quickly. So 1/2 times 1/4 is an 1/8. We're still going to have volt seconds per amps here. I'm just lumping those guys together. I'm going to have 7 times 7 is 49 amps squared. 7 times negative 5 times 2, so that's negative 70 e to the minus 4t amps squared plus 25 e to the minus 8t amps squared. Are we okay with me expanding I squared to get that? Anybody have any beef with what I've done? All right, so let's look at the units here really quickly. So my amp here is going to wind up canceling out one of the amps in the amp squared in the numerator. So dimensionally, I'm going to have volts times amps times seconds in the numerator. What's a volt times an amp again? A watt. And what's a watt times a second? A joule. So we're going to wind up with energy, which we should expect because we're determining the energy stored by our inductor. So units are important, all that kind of good stuff. So pretty obviously here, then we're going to have 49 eighths minus 70 eighths e to the minus 4t plus 25 eighths e to the minus 8t joules. So I think I would be correct in saying that the biggest pain in the ass for this particular problem was actually just figuring out what the inductor current was. And once we had that, everything else is pretty straightforward. And that will generally be the case. All right, so I realize that I have talked for 70 minutes straight, so I promise I'm going to stop talking within the next 10 minutes, but we do have one more smallish thing I want to cover, and that is how we combine inductances, because we will deal with circuits that contain multiple inductors at times. Okay. I will probably only fully derive one of these. So let's look at inductors in series because it's not particularly difficult. So let's say that I have a network containing multiple inductors in series. So we have L1, L2, all the way out to some inductance L sub n, like so. We're part of a larger circuit that has some total voltage V of T across it. And because all of these inductors are in series, they'll have the same current I of T flowing through them. And what we're going to wind up doing is Kirchhoff's voltage law here, much like we did when we had resistors in series. So I'm going to go ahead and define the voltage drops across my inductors like so. So this will be VL1, VL2, all the way out to VLN, like so. And we can say, using Kirchhoff's voltage law, that the total voltage drop is just the sum of the voltage drops across our inductors. We know that the voltage drop across an inductor can be expressed in terms of the inductor current. So this could be written as L1 times the derivative of I with respect to time plus L2 times the derivative of I with respect to time, all the way out to L sub n times the derivative of I with respect to time. And since we have a common factor of the derivative of I with respect to time, we can just effectively factor that part out. And we'll wind up with L1 plus L2 plus L sub n times the derivative of I with respect to time, or LEQ times the derivative of I with respect to time, where LEQ is just the sum from I is equal to 1 to n of all of our inductors in series. Or in a much more succinct way, inductors in series combine like resistors in series. So without doing any math whatsoever, because I can tell that you guys are very bored with me today, Ashton included, it's okay. How do you think inductors in parallel are going to combine? Like resistors in parallel. Great, we don't need to do any math, we've got it. All right, so that's enough out of me for today. So our next topic for today's Wednesday, right? So our next topic on Friday will be an exploration of capacitors and capacitance. We are going to go through it incredibly quickly because I am effectively going to give you the exact same lecture, except that I'm going to swap I and V, and everywhere I had L but C, And that's how capacitors work. So instead of spending 75 minutes, we'll spend 30 doing literally the same damn thing. All right, I'll shut up now. Yes, ma'am. Fantastic question. Let me pull up WebWork really quickly, and I think we can make that distinction rather easily. And I know it's going to sound easy and trivial because it is, but I genuinely believe it is a good question.
For their cameras, do they have to install fallback diodes?
I don't know. I did it. I didn't teach 121 when they were doing the canister oven. I taught it when they were doing the fish tank, which we definitely use diodes in, and MOSFET.
Yeah.
So I think this is homework set number 11, if memory serves me correctly. All right. So let's look at this circuit right here, shall we? All of our sources, V1, V2, and V3 are defined to be DC voltages. So this is a DC circuit. Now, if we look at our next problem, which of course, so this one right here, the graph is current. Is the current changing in time? This is an AC circuit. That's it. So if the sources are DC sources, it's a DC circuit. If the sources aren't DC sources, it's not a DC circuit. Yep.
You showed a video where they try to remove current and then like parts. In my life, I don't I remember that. I feel like he showed us like a Faraday ball here, but we were like parts.
I'm trying to think of what that might have been.
Maybe it was like they gave us a label. I don't know, I think I remember.
Yeah.
I just think it was cool. Clearly, I remember it.
Yeah, these are all high power things, but these are shorts, yeah. Yeah, so this video is effectively what, holy God. How do I? Okay. This is at a power substation, and this is a disconnect switch where they're trying to interrupt the flow of current between 2 points where we have all of these nice surge arresters and all that kind of stuff that behave like inductors and things. And so trying to change the current abruptly literally causes almost a lightning strike to occur because that's how bad the current wants to continue to flow in the system. That actually happens in every light switch and everything like that we have, which is the reason they have protective plastic plates on top so that you literally can't see the sparks and all of that kind of shit that's happening inside. It's also actually why light switches have a spring to make sure that it goes all the way from the off state to the on state and the on state to the off state as quickly as possible. Because if you were allow it to stay in that middle state, it could actually fuse the switch closed or open and damage it. So there's a spring in there to make sure that it snaps and clears that discharge as quickly as possible. If you're a nerd and like to know how stuff works.
Well, it's just like practical.
It is, yeah. I used to talk about unplugging a hair dryer. If you leave your hair dryer or something like on, that's a hair dryer has a small induction motor in it and all of that kind of stuff. And so if you just pull it out of the wall while it's on, you're very likely to see sparks and all of that kind of stuff because it's trying to keep that current flowing, even though you've unplugged it. Don't do that, by the way.